Okay, well, thanks for coming along to tonight's talk. I'm Ian Lauwerys. I'm a member of North Essex Astronomical Society. We do try to do these talks once a month, but it depends whether we can get a speaker or if other things get in the way. We will be tonight talking about observing the sun. So I subtitled this From Beginner to Expert in quotation marks. I know a bit more than I did when I started. I wouldn't want to call myself an expert, but we will look at some of the more advanced things that we can do in terms of observing the sun. Okay, so let's start with slide one. So I'm going to tell you a bunch of different things. First of all, I'm going to tell you about how to stay safe when observing the sun. I think this is really important because the sun can be quite dangerous. We'll look at what the nature and structure of the sun is, not in a huge amount of detail, but just enough so that it will help us to understand what we're looking at when we actually start observing the sun. Then we'll have a quick look at some simple things that kids and young people and old people such as myself can do about using the sun to tell the time. We'll have a look at observing the sun in white light, how to do it safely and what you can see. We'll have a quick look at eclipses and planetary transits, something that many of you are familiar with. And we'll talk about when and how to see them. Then we'll move on to looking at observing the sun in other wavelengths, particularly hydrogen alpha. And that helps us to understand some of the powerful dynamic forces that work on the face of the sun. Finally, we'll just have a little bit of a chat about imaging the sun, not in great detail, but if anybody's interested, we can talk about that more at one of our weekly imaging meetings. By the end of the talk, I hope you'll have a slightly better understanding of our nearest star, what makes it work, and as well as particularly knowing how to observe some of its fascinating features quite safely. So onto the boring Patrick Moore bit that we always have to do. I have to say, just in case anybody's watching this on YouTube, I'm sure that most of the members of the society are well aware of this, but it isn't always obvious if you're not an experienced astronomer. Never look at the sun through directly through a telescope or a pair of binoculars. Don't look at it with the naked eye. If you look at it inadvertently, it's not a problem, but definitely don't stare at it. The problem is the sun's surface is about 5,500 degrees Celsius. That's literally hot enough to melt anything. If you focus that heat on the back of your eye, you'll burn your retina and you'll damage it pretty much instantaneously, irreparably. We do have a blink reflex that causes us to close our eyes and look away if the sun is really bright or something else bright shines in our eyes. And under normal circumstances, that will protect you. So if you accidentally catch the sun when you're not intending to look at it, it will prevent you from getting any permanent damage. I mean, I should say that's with the naked eye, but you could, some people might decide to try and stare at the sun deliberately. It's really not a good idea, even without a telescope. Sunglasses are no protection. The point is that the heat that particularly that a telescope or a small pair of binoculars collects is all focused onto one small spot on the back of your eye where the image of the sun is appearing, and it will actually burn and kill the cells there, you know, within a fraction of a second almost in some cases. You really wouldn't feel that because there's no pain sensors in the back of your eye, so you wouldn't know what's happening. And the first thing you would know is that you have a blank spot in your eye, or that you would actually not be able to see at all, and it's too late. Once you've damaged your eyesight, you cannot fix it. It is a permanent problem you will never recover from. So please do not ever look at the sun through a telescope or binoculars. You've one pair of eyes, please take care of them. Just to make the point, this is a steel plate, quite a nice thick steel plate, and it's purely being melted by the heat of the sun. Just a big mirror collecting the sun and focusing it onto one spot on a steel plate. It is a big mirror, to be fair, but you know that will take a few seconds to melt solid steel. You really don't want that to the back of your eye. So safety first, only use equipment that's been designed specifically for safe solar observing. We'll talk about some of that today. Check that your equipment is in good working order every time that you use it, and make sure that you follow the instructions that the manufacturer provides. There is a lot of very unsafe old equipment. Again, we'll talk about some of that might be knocking around in attics and dusty old sheds. Don't be tempted if you're unsure. Please ask us for advice. We'll tell you whether something's a good idea or not, and usually it isn't. And particularly, don't leave your equipment set up unsupervised even for a moment. Small children and other individuals, vulnerable individuals, are often curious, and it literally will only take a second for them to look through a telescope when you're looking away, the damage is done. If you've got a solar filter on your telescope, that's fine, but just remember the finer scope and any other small telescopes are just as dangerous, so either remove them or cover them up securely before you start observing. Okay, so let's talk about what the sun is. Now, most of you will know that the sun is a star. It is literally just like all of the other stars that you see at night. The only difference is that it's a lot nearer to us than those stars. It's a fairly ordinary star. It's about 4.5 billion years old, so it's about halfway through its life. It is actually brighter than about 85% of the other stars in our galaxy, but it's still a dwarf compared to the largest and brightest stars, which can be over 100 times bigger than the sun. But it is bigger than 85% of the stars in the galaxy. There are lots of smaller stars, particularly red dwarfs, which are really tiny. There are loads of those. So the sun it's big, but it's not exceptional. It's fairly ordinary. What is a star, particularly the sun? Well, it's a sphere. It's just a big sphere of gas, mainly hydrogen and helium, in the form of plasma. Now, plasma is just really hot gas. It's in a state where the molecules of gas have been ripped up, so the electrons have been ripped off from the protons, so that it's electrically charged. But it is just gas. It's the same stuff as we have on Earth. It's hydrogen on Earth, which is very common. It's the most common element in the universe, and every molecule of water on Earth has one hydrogen atom in it and two oxygen atoms. So there is a lot of hydrogen here. Very easy to get hold of, very easy to make. The second most common element in the universe is helium. That's also in the sun. There's quite a lot of helium in the sun, but nowhere near as much as there is hydrogen. It's the second lightest element in the universe, and it's also quite common, but there isn't very much of it down on Earth. It doesn't react with other elements. So hydrogen reacts quite readily. It reacts with oxygen, so it'll make compounds. It'll make water. It'll make other hydrogen compounds. It'll make hydrocarbons, petrol and diesel, that kind of stuff. Helium doesn't react with anything else. And it's really, really light. So it literally floats up to the top of the atmosphere. Oh, sorry, 2 hydrogens, H2O. Sorry, someone's telling me, Chris. Sorry, Chris, you're right. Wrong way around. It's 2 hydrogens, one oxygen. So helium is the second most common element. It's the lightest element, second lightest element. It literally floats out of the atmosphere and off into space. If you ever have one of those helium balloons when you're a kid, you let go of it, it floats up in the air. That's exactly what happens to helium. It literally goes up to the top of the atmosphere and boils off. So there isn't much of it knocking around. Most of the helium we have on Earth is actually made through decay of heavy elements in rocks, where the helium's trapped, and then we later extract it in natural gas. There's a few places on Earth, particularly in Texas, but there's a few other places where we get helium, but it isn't very common. So most of the hydrogen and helium in the sun is in the form of plasma. The sun's really big. It's about 1.39 million kilometers in diameter, and it has a mass of, I'm not even trying to read that really big number out on the screen, but you can see it's a really, really big number of tons. It is huge. And the sun's powered by nuclear fusion. So what does that mean? Well, the immense heat and pressure inside the sun squashes all those hydrogen atoms together, and under that heat and pressure, after jumping through a few hoops, we turn 4 hydrogen atoms into 1 helium atom, and in that process we release some energy. So that's called nuclear fusion. That happens in the sun because it's really hot and there's a lot of pressure there, and every second about 600 million tons of hydrogen is fused into helium, and about 4.26 million tons, so 4.25 million tons of that matter that's going through fusion is actually turned straight into energy. So, and that's quite a lot of energy. But whilst it sounds like the sun might be going through its fuel at a very alarming rate, going through 600 million tons every single second, it actually take about 105 billion years to convert all of the sun's mass from hydrogen to helium. That's 7 times the current age of the universe. So actually, whilst we're converting a lot of matter every second, the sun is so big that it wouldn't run out quickly. In reality, only the hydrogen in the sun's core can actually be converted, and that's a lot less than the total amount of hydrogen in the sun. So actually, the sun's lifetime is expected to be about 10 billion years. So it's about a tenth of the stuff will be converted from hydrogen to helium. That's still a really, really long time. The universe is only 13.8 billion years old. So, you know, sun living 10 billion years, you can see that's quite a long time, but it's still, you know, it's still relatively short compared to the expected age of the universe. So we're basically, the power of the sun comes from nuclear fusion, turning hydrogen into helium, and in that process, some energy is released from converting matter into energy. When we look at the sun, and here's a bit of a picture of the sun that I made in my 3D thing. These are actually pictures that I took of the sun. It's not quite to scale, but just to give you a bit of an idea. If we look inside, the sun's a bit like an onion. It's got different layers. So in the center, we have the core. This is where the fusion is happening. And this has a radius of about a quarter of the size of the sun. The temperature in there is about 15.7 million degrees Celsius, which is really hot, as you can imagine. And that's where fusion happens. And that's where all of the energy comes from that powers the sun. It's also where most of the energy that powers life on Earth comes from, through the form of sunlight coming down through the atmosphere, going into plants, going into animals, going into bacteria. There are a few other ways that life can get energy on Earth, coming from materials under the sea, etc. But most life on Earth is powered by the sun. So all of that energy is created in the core through fusion. We can't really do fusion easily on Earth in a controlled way. We can make big explosions through fusion, but the problem on the Earth is that we don't have the pressure. It's not just a really high temperature of 15.7 million degrees that makes fusion happen. It's also the pressure from all of the stuff. Sorry, just go back a slide. Pardon me. All of the pressure, all of the mass of the sun pushing in, squashes stuff together. That's why trying to do controlled fusion on Earth to create energy here is really, really difficult, because we can't create that pressure. We have to increase the temperature to compensate. So where nuclear fusion in the sun can happen at about 15.7 million degrees, we'd have to do it at about 100 million degrees on Earth, because we don't have the pressure to squash stuff together. So we actually have to increase the temperature instead, and that's pretty hard to do. And there are lots of experiments being done, but we haven't quite got there yet. It's always, 10 years away. It has been my whole life, and I suspect it will be. If we ever get there, then it will be great, because our energy problems will be over, but it's quite a hard problem to solve. Okay, so all the energy is being produced by fusion. Now, the actual energy produced by volume is a lot smaller than you might think. So the sun produces about 277 watts per cubic meter in the core. And that doesn't sound like a lot, and it isn't a lot. It's pretty much the same amount of energy that your garden compost heap produces. So inside your compost heap, you have bacteria chewing away on all the decaying plant material. And as they do that, they generate heat. And as any keen gardener will tell you, if you dig over your compost heap, you'll find that it's really hot and warm inside if it's working properly. So the sun, the core of the sun, is actually producing about the same amount of energy as a compost heap by volume. It's the massive size of the core and the immense pressure and density that traps the heat, which is why it gets so hot. Why your compost heat doesn't go up in a massive bang is because the heat escapes quite quickly. In the sun, the heat is trapped inside the core for a very long time. So that's the bit in the middle. That's where all of the action is. That's where all the energy comes from. Next, we have what we call the radiative zone. Temperature at the bottom of the radiative zone, just above the core, is about 7 million degrees. And near the top, it drops to about 2 million degrees. But the only way energy can travel through this zone is through photons of light. So essentially, light being emitted by an atom, and then being absorbed by an atom, and emitted by an atom, and absorbed by an atom. And the light is bouncing around inside the radiative zone. It's trying to get out to the surface, but quite just as often as going up, it goes back down again. And given the density, it can actually take a really long time. So a single photon of light that leaves the core can take about 100,000 years to make its way out to the surface of the sun, because it's just following this really long wandering path, and it's constantly being diverted off in different directions. Once it escapes from the surface of the sun, it'll only take about 8 minutes to get to the Earth. But the light that you see during the daytime on the Earth might only take 8 minutes to get from the sun. That's taken an average of about 100,000 years to make it from the core to the surface. So it's actually quite old. Now, the remaining third of the sun's radius, from the top of the radiative zone to what we'd effectively call the surface, so there isn't really a surface because we're talking about a big ball of gas here, is called the convective zone. Now, The convective zone acts a bit like a lava lamp. What's actually going on here is the photons of light and energy that are coming out of the radiative zone eat the material at the bottom of the convective zone, and as it heats, it becomes less dense and it rises up through the convective zone to the top, where energy escapes out into space. That cools the material and it sinks back down again. So if you've ever had one of those 1970s lava lamps, that's exactly what's going on there. You have some waxy stuff that gets hot at the bottom, floats up to the top, cools down, and sinks again because it gets more dense again. The same thing's going on here. Only that top third has convection going on. The density and the rate of heat transfer through the radiative zone is such that no convection happens here. It only happens in that top third. It varies by stars. Red dwarf stars, which are much smaller, the whole star pretty much has a convective zone and no radiative zone. And that means that the material is recycled round and around and around. So all of the hydrogen in a red dwarf can actually be used in fusion eventually. And that's why they live vastly longer than ordinary stars like the sun, where you can only really fuse the stuff that's already in the core or very close to it. There isn't much mixing going on. Okay, so the convective zone actually consists of this huge number of convection cells all over the surface. They're going up and down, and that has an interesting consequence, as we'll see later. And above that, we then have what we call the photosphere. So that's the bit, as we'll see in a bit, where we see things like sunspots. Photosphere literally means light sphere. It's a layer that's only about 100 kilometers thick, and this is where light is that visible light is actually emitted. So at the bottom of the photosphere, what actually happens is that hydrogen atoms gain a second electron. They become what we call hydrogen anions. So effectively, they're negatively charged hydrogen atoms, and that in that process, that photon of light is emitted, and that's what escapes up towards the surface. At the top of the photosphere, as I've said, this is the bit that we see of the sun during the day. The temperature is about 5,500 degrees Celsius. Then above the photosphere is another layer which we don't normally see unless we use some special equipment, is the chromosphere. This is called the chromosphere, the color sphere. This is about 2,000 kilometers thick, so it's much thicker than the photosphere, but it's also quite a bit thinner. It's a similar temperature, obviously, at the bottom of the bottom of the photosphere, and there are areas where it's cool enough actually some simple molecules can form, atoms can actually start bonding together to make molecules. But near the top of the chromosphere, the temperature gets up to about 20,000 degrees Celsius. It's actually hotter further away from the sun. It's the center, which might sound counterintuitive, but actually some interesting stuff that goes on in terms of energy transfer with magnetic fields and things. That actually means that the thinner gas further out from the surface of the sun is hotter than the stuff that's lower down. So we mainly from the Earth see the photosphere and the chromosphere. And finally, not shown on the diagram here, we have the transition region in the solar corona, which is a really big, diffuse bit of the sun's atmosphere. It's much, much bigger than the photosphere by volume. It's got a greater volume than the whole of the rest of the sun, which stretches way out into space. We can't normally see it. We can see it when there's a total solar eclipse. It appears as a big white sort of halo around the sun with lots of features in it. The corona is really, really hot, actually. It's about 1 to 3 million degrees on average. In some places can actually get up as hot as 20 million degrees, so it's actually hotter than the core, which might sound surprising given that, again, you think things are further away you get from the heat source, the cooler you think things would be. But actually, magnetic fields, we believe, transfer a lot of energy up into the corona and heat it up. Okay, so that's the basic structure of the sun. I've put on the diagram a tiny little P down here. That's the Earth scale. The Earth is really small compared to the sun. All of the planets are. So if you've got any young people, I'll just nip through this quickly. The first thing that anybody should think about when they're observing the sun is building a simple sundial. It gives you an idea of how the sun moves, gives you an idea of how to measure time. It's dead simple. Put a stick in the ground. If you're in the northern hemisphere, slant it slightly towards the north. If you're in the southern hemisphere, slant it slightly the other way towards the south, so it casts a better shadow. And then every hour, just come out and put some markers on the ground where the sun is, where the shadow of the stick is, should I say. And you can see that as you do that, you'll find that you're marking out the hours, and you can even write the number on it. I've used a flower pot, you could use stones, you could use anything really. Now, if you then have a problem with your digital watch or your calculator, or the internet dies or whatever it may be, you can just pop out into the garden and have a rough idea of what time it is. So it's a very simple clock, but it's also one of the oldest. It's a really straightforward idea. The oldest sundials we found were actually about 3,500 years old from ancient Babylon, but I think it's fairly safe to assume they've been around a lot longer than that, because it's such an obvious and useful idea that anybody who needs to have a rough idea of the time can make one. I would guess you can also, if you're a good outdoors person, as I imagine most of the ancestors would be, you'd have a fairly good idea just by looking in the sky at what time it was. But once you start having towns and villages and things, this kind of stuff becomes more useful to organise people. It's not very accurate though. You can make a much more accurate sundial quite easily. We can make what we call an Analemma sundial. Now, there are lots of different designs of sundials you can build, but this is one of the simpler, easier ones to understand. So I've actually put on our website on northessexastro.co.uk. If you look under the free astronomy resources section, there's actually a template for making your own Analemma sundial, and it is very accurate if you do it right. You just need to print out the sundial, and then you just need to make a little triangular bit that's also on the page, print it out, cut it out, stick it on in the right spot. You've now got a sundial that's designed for Colchester that's very, very accurate, but it will be accurate to within 3 minutes anywhere in Essex, or anywhere in the same longitude in the Northern Hemisphere. The key thing is you need to make sure that when you set your sundial up, that it's flat on a flat surface, and that the style and the little north arrow on the page are pointing due north towards Polaris. Not ideal if you're trying to set it up during the day, because obviously you can't see Polaris. You can use a compass or a compass app on your phone. Fortunately, in the UK, particularly in Essex, the difference between magnetic north and true north, where Polaris is, it's not that great. It's not very much at all. Other parts of the world, there's a big difference, and you have to correct for that. But here, there isn't really a problem. Once set up, you can really use the sundial to tell the time very, very easily. You just follow the pointy shadow, and when the pointy shadow is touching one of the lines, you follow it down to the bottom, and that number there tells you the hour of the day. The important bit is that between June the 20th and December the 20th, you use the green lines that I've printed on there for you, and between December the 21st and June the 19th, use the grey lines. So that, I'll explain why in a minute. It's also worth bearing in mind that sundials only show the time according to the sun. They don't know about GMT in summertime. So you need to add an hour between March and October, when summertime is in effect, to the time the sundial shows. The sundial only shows hours, because otherwise you'd have too many lines on here. To estimate the minutes, you just need to roughly guess how far the pointer is, shadow is between the two pairs of lines. So it's halfway between two lines, then it's half past the hour. Why does it work? Well, it's called an Analemma sundial, because if you take a photograph of the sun, as we've got here, from the same spot at exactly the same time every day, or numerous days throughout the year, you'll see that the sun traces out this big figure of 8 shape, which is called the analemma. Now, this is only true if you make sure that you stick to one time method. So you use GMT to measure your time for taking your photographs. If you use BST, then it will go wrong. Just stick to GMT through the whole year. If you actually then think about it, if the sun's making these movements through the sky, the shadow of the style on the pointer on the sundial would also make a figure of an 8, and you can test that yourself again if you're patient. Put your stick in the ground, and then the same hour of every day for a year, just go out and put a little mark on the ground where the end of the shadow is, and you'll find that it draws an analemma on the ground. And now you can see that if you look at the sundial, that all we've got is we've just got the analemma drawn for every hour of the day, and that will actually correct for the fact that a normal straight line sundial without the analemma on it can be wrong by as much. Let me just check for you here. It can be wrong by, I think it's about 14 minutes to 16 minutes fast. I think it's 14. Yeah, 16.5 minutes fast or 14 minutes slow, depending on what time of year it is. So, you know, you can have got a half an hour error with a straight line sundial. The analemma is much more accurate down to the minute for the hour. And this is simply because the Earth is going around the sun. It's got its axis tilted over, so it's pointing away from the sun during winter in the northern hemisphere and pointing towards it in the southern hemisphere, towards the sun in summer, and the opposite is true in the southern hemisphere. So in the winter, the sun is down here at the bottom of the analemma in the northern hemisphere. In the summer, it's up here high. And we're also going around the sun, and our orbit around the sun isn't quite circular, it's a bit egg-shaped. So we get a bit closer and nearer, and the combination of those two things makes the sun move side to side a bit through the course of the year, a given hour of the day. So that's why we get this figure 8. We've also adjusted our sundial because we have time zones now. In the olden days, when people didn't really care, and there was no fast communications, every town just set their time by reference to the sun. They'd have a sundial, or they'd just have somebody who'd measure it for them. They'd set the town clock, and everybody set their watches from it just by reference to local noon. So you'd have a different time of day depending on how far east or west you were in the UK or anywhere in the world. It didn't really matter in those days because the fastest you could go was horseback. So the only people that really cared were astronomers and sailors, and other than that, normal people didn't care. Once railways came in, people could travel much faster from place to place, and the only way you could have timetables that worked was if you had standard times everywhere. Not that the timetables seemed to matter either. But so now in the UK, everybody uses Greenwich Mean Time, which simply means that everybody sets their clock by noon at the Greenwich Meridian in East London. Now, Colchester is about 0.9 degrees east of Greenwich on the face of the Earth, so we have to tilt our lines over a bit to correct for that. Otherwise, we'd be about 3.5 minutes fast. So this is a super accurate sundial for Colchester and pretty good for the rest of Essex. There's a little URL link on the actual sundial template if you want to make your own. There's free software. It's a little bit tricky to get going, but you can make your own sundials. Again, if you've got kids, I won't labour this one. It's fairly straightforward experiment. You can make a pinhole camera to observe the sun safely. You just need a cardboard box, cut a hole in the front, cut a hole in the back, cover the back with something like tracing paper or greaseproof paper, or in the worst case, as we've done here, a bit of baking parchment. It's not as good as tracing paper. Cover the front with hole in the front with a bit of tin foil. Make a small hole in the tin foil with a pin or a needle or something. Then when you point the pinhole camera up at the sun, what you'll find is on the screen at the back, you'll get a little picture of the sun projectors. That's not a sort of dot that's caused by the pinhole. That is actually the sun's disk. I can prove that. Here's a picture of a light bulb filament that I took using the same pinhole camera. Here's a picture of a window frame that I took using the pinhole camera. The only problem with the pinhole camera is it doesn't magnify and the image is quite dim, but it's a fun little experiment. If you've got 5 minutes and you're feeling a bit arts and crafty, then give that a go. If you want to go a little bit further, you can actually get a thing called a solar can, which is a really fun experiment. They cost about £16 to buy. You can set them up for days, weeks or months. I mean, really all they are is a tin can with some light-sensitive photographic paper wrapped around the inside, and under the sticker there's a little pinhole. You set up your solar can by cable tying it to a post or a drain pipe or something, pointing towards the south. Peel off the sticker and then leave it for as long as you can get away with, up to months. The sample picture is about 4 months worth, and you'll see the journey of the sun across the sky every day and how it changes from month to month. You'll also see when it's cloudy because there's no sun and when it's sunny. Once you've actually finished exposing it, what you do is take it indoors. You go into a nice, not too bright room, take the top off the can with a tin opener, take the photographic paper out and you put it on your scanner, and you scan it or you photograph it to preserve the image, because after a few minutes the light will destroy the image and you get a lovely picture. So that's another great fun experiment that you can do. Keep you entertained through lockdown. The other way you can observe the sun very safely if you've got kids or if you just don't have the equipment is to use what we call Eclipse or solar glasses. They're fairly cheap. They're only about £3, and you can buy them in bulk if you're doing it for a school or something. The key thing is they must be CE certified to the ISO 12312-2 2015 standard, I know it's a mouthful, but that means it's safe. And you should really only buy them from a reputable retailer, like a proper astronomical retailer. You can buy them on Amazon, you can buy them on eBay. They do try to stop people selling dodgy stuff on there, but personally, I wouldn't risk my eyesight. I would go to a reputable supplier and buy them there. I wouldn't buy them off eBay. I definitely wouldn't buy them off a Facebook ad. Every time there's something exciting going on the sun, the scammers come out, they start selling all sorts of junk, and they can be dangerous. Always check there's no holes and tears in the lenses before you use them. Make sure that if they are damaged, you destroy them immediately. You can get adult and child sizes. So if you've got children, get small sizes. They're great for partial and total eclipses, which we'll talk about. And you can see the largest sunspots as well with them. So don't think you need lots of really expensive equipment. But equally, please do not try anything else. Sunglasses, silver foil, plastic filters, photographic film, all of the nonsense that people have talked about and often post on social media. Please don't try it. Only safe solar glasses from a reputable astronomical retailer. You can also do solar projection. There's a safe way to do this, and you can get these little solar projectors. This one's about £25. It comes in this little cardboard kit with a couple of mirrors and lenses from Astromedia shop. The link is here. Again, if anybody needs it, please either just post on our Facebook page or contact us through our email. Gives you a much larger view. So it's a bit like the Pinhole camera, but it magnifies the view, so you get a nice view of the sun. It's quite safe. They're although it's made from cardboard, it is fairly sturdy, and it's a fairly cheap way for a group of people, you've got a family, to observe the sun quite safely. There are much more expensive, sort of £200, £300 solar projectors available, but this is pretty good, if you want to do something fairly cheap and easy. Now, I'm going to talk about this for purposes of telling you that it's hazardous, not because I think it's a good idea. You will see in lots of astronomy books, and particularly in older books, that you can project the image of the sun using a telescope. You certainly can do that, but it is very hazardous. There are all sorts of problems, and some of them are not that obvious. First off, there's a real risk of damaging people's eyes if you get it wrong. There's also a real risk of damaging your equipment. You should really only use small telescopes, less than 80 millimeters. Anything bigger than that will gather an awful lot of heat, and it needs to be a refractor. Don't use a Newtonian, don't use an SCT, don't use a Mac, and don't use anything with lenses at the rear end, like sort of high-end petrol type refractors, because all of those can be damaged by the heat of the sun that's collected inside the telescope. No cheap telescopes with plastic lenses or parts, as they may melt. And beware, the eyepiece is always at a level where young children and animals' eyes are, and your legs are also there, and you can quite happily set fire to your leg if you're not careful. I really wouldn't recommend doing it. There are much safer ways of observing the sun in white light, and we'll talk about those in a minute. I will give this a miss. I'm just telling you, you can do it, but you shouldn't. It really isn't that safe. The most dangerous thing you can do is to use an eyepiece solar filter, a bit like the ones we see on the screen here. One of these is an old one from back in the sort of 50s and 60s. It would have come with your telescope. And the new one, horrifyingly, is available to buy online these days from various sites. These things, A, are not necessarily safe. They don't necessarily absorb enough light to protect your eyes from being damaged. But the real risk with them is that they can get very, very hot. And as they get hot, they can crack, they can split. And if they split open while you're looking through the telescope, the light is going to go straight in your eye and it's going to blind you. So do not use any kind of eyepiece solar filter. Really, really not safe. Safest way to observe the sun in white light, and it is remarkably cheap if you've got a pair of binoculars or a small telescope, is solar film. So Barda Planetarium is one of the manufacturers, the one we recommend, because we know that they test their stuff in Europe to high safety standards. There are other manufacturers of solar film. I'm not saying they're not good, but we don't know necessarily. They don't publish their test results necessarily. We know these guys do. They make a big thing of it. The stuff you want is called Barda Astro Solar Safety Film. It's the one with the blue bit on the top of the packaging. There's also Astro Solar Photo Film, which has a red bit on top. It's about the same price, but it's not suitable for visual. It's only suitable for photography, so don't use it on your telescope to look through it. Make sure you buy the Astrosolar stuff. It's about £18 for an A4 sheet. Comes in larger sizes as well. It's a really tough plastic film that's coated on both sides with special reflective layers, and it just comes as a layer of film with the instruction. And as you can see from the photograph, what you do is you make your own filter holder out of cardboard and sticky tape, and what happens is it will block 99.999% of the light before it goes in the telescope. The key thing is you make your filter holder nice and sturdy from cardboard, and if you're putting it on the telescope, I would recommend actually using a bit of tape to hold it on to make sure it doesn't drop off while you're looking through. You can see here that the film looks a bit wrinkly, and that will tell you that in the instructions. That's correct. You don't want to stretch the film really taut because that actually damages the view. It makes the view not very good. If you put it in slightly wrinkly like this, it might sound wrong, but actually that's how you get a good view through this stuff. The only thing you really need to do is make sure that you hold it up to the light and have a good look through it. Make sure there's no tears and no big pinholes in there, and it's not coming apart before you start using it every time, because obviously it's not very sturdy. This stuff will allow you to see lots of sunspots and other features we're going to take a look at in a minute. If you want to spend a bit more money, 70, 80 quid maybe to £100, you can get the same sort of thing in a glass filter that will fit on a telescope. It does exactly the same job. The view will probably be yellowy orange rather than white, because the filter coatings are slightly different, but it's still a white light filtering that shows the same features. Basically does the same thing as the Astrosolar film, it's just a bit more robust. Final way to view the sun safely in white light is to use a thing called the Herschel Wedge. Now, these are quite a bit more expensive, and they're only really suitable for small refractors. They're not suitable for SCPs, Macs, or other big Newtonians, because A, there's too much light going into the scope. Again, the same problem, you can damage the internal optics of the scope. So you only want a small refractor where the light is going straight to the back. And what happens with these is you have a glass wedge inside the body of the filter, and about 95% of the incoming sunlight goes straight through the wedge into a heat absorbing plate at the back of the wedge, and about 5% of the light is reflected upwards into a second filter, which doesn't get too hot, and about 0.001% of the light goes through that filter, and that's what you observe. So again, it's a pretty safe way for a small refractor. It's nice and robust, it's nice and solid. It potentially gives a slightly better contrast, a slightly better view than a front-mounted filter on a small scope. It's quite portable. So, horses for courses, but all those three methods, so solar film, glass filter, and Herschel Wedge, will give you the same features on the sun. If you're observing in white light, one thing you can do is use a thing called a solar continuum filter. It's basically a green filter, and it improves the visibility of some of the features we're going to have a look at, because it blocks the red and green light and only lets red and blue light and only lets green light through. That A increases the contrast, and B means that you've got less light wavelengths to focus, to potentially get a sharper image. At about £80, depending on size, you must use them with a solar film, glass filter, or Herschel Wedge. They're not to be used on their own. They're just an aid to using one of those filters. So in white light, what can we see then? If we look at the sun through any of those white light filters, what you will see is what we talked about, the photosphere. This is the nearest thing to the sun has to a surface, but it's not really a surface. You should really think of it more like a sort of layer of really dense fog rather than a solid surface. So it's literally called photosphere, the light sphere. And what we're looking at is broadband emission, i.e. white light coming from the sun's plasma. Now we tend to think of the sun as being yellow, but it's not. It appears yellow, perhaps sometimes to our eyes, in daylight, simply because the blue light that's in the sun's white light that's hitting the earth is scattered through the atmosphere. That's why the sky is blue. And that deficit of blue light coming from the sun, because it's been scattered all around, actually makes the sun appear slightly yellowish in certain conditions. So we tend to think of it as yellow, but it is actually pretty much white. Again, it's called a yellow dwarf for classification purposes, because it is strongest in that kind of that wavelength because of its temperature, but pretty much it is a white light object. It emits all of the visible wavelengths and lots more besides. So the light that's coming out of the sun is white. So that light is being emitted from the photosphere, but whilst the photosphere, as I said, appears to be solid, it's actually a layer about 100 kilometers deep of sort of increasingly dense fog almost, and it's partially transparent down to a depth of about 2/3 of that 100 kilometers. If we look at the sun, you can see on this picture, and it's not an optical illusion, that around the edges, the disk appears slightly darker than it does in the center. And that's a real effect called limb darkening. And that's simply because when we look right at the edges here, we're actually looking through the fog and back out into space. And when we're looking in the center, we're looking through all of the layers of the photosphere, plus we're actually looking, it's brighter as well. There's two different, it emits more light at the lower layers, which we're looking into, and we're looking through more layers. So literally we have this, what we call limb darkening. So we have this effect, the sun appears brighter in the middle and it's darker out towards the edges. That's a real effect, that's not imaginary. It looks like a bit of optical illusion sometimes. It can be a bit hard to notice at first, but once you've seen it, you know it's there. It's pretty easy to see. Now, the next thing that you'll see on the photosphere, if you've got a big enough telescope, is what we call granulation. So we talked about convection. There are big convection currents inside the sun where hot gas is rising, cooling, and then sinking again, hot plasma. But at the surface, we have convection going on as well. And there are lots and lots of these convection cells where bubbles of hot gas and plasma are rising up to the surface. Each of the granules, each of these bubbles is about 1,000 kilometers across, which is pretty small, but the sun's really, really big. So with a reasonably high magnification and an aperture of about above 80 millimeters with a reasonably large telescope and a bit of magnification, you should start to see the granulation. So the picture at the top is pretty much what you'd expect to see through a sort of small to medium-sized telescope, these speckly appearance. Granules last about 20 minutes in the plasma. They rise up, they cool, and then they sink. They're moving at about 36,000 kilometers an hour, so they're going pretty quickly. You get a professional telescope, you get a view that's more likely to get more contrast, more magnification. You get these granules. To just show you, really, we've got what we've got here. This is an animation of the granulation. It's speeded up, but it's in process. You can see the bubbles are rising and then sinking at the edges. This is a not speeded up video of my dinner cooking a couple of days ago. And basically it's the same thing going on here. We've got hot bubbles rising up to the top. In this case, it's steam, but the water is also rising, and then it's sinking back down to the bottom again. And it's the same process that's going on over the whole surface of the sun. As I say, you won't kind of see this fantastic sort of motion going on, but if you look through a moderate sized telescope, so I go back to the previous slide, you will see the granulation, and the more magnification you put in, the more apparent the granulation becomes. The most exciting feature of the sun that we can see in white light is sunspots. Now, sunspots have been a bit rare recently, but they're starting to reappear again, and that's because of the solar cycle, which we'll talk about in a minute. They're basically places where the sun's magnetic field pokes up through the photosphere and out into space. What actually happens is that the magnetic field is coming out, it pushes aside the rising gas that's coming up, the plasma that's coming up under convection, and so no new hot material is coming up to the top. You actually see the cooling happen. So in the center of the sunspot, you get this dark area called the umbra, and that is, it appears dark only because it's cooler than the surroundings. It's actually about 3,500 degrees Celsius is the average temperature of the umbra, the dark middle of the sunspot. So it's about 2,000 degrees cooler than the surrounding photosphere. So that's why it appears dark, but it is still really hot. Now, around the umbra, you'll often see a grayer area called penumbra, which is, as the name suggests, it's sort of slightly warmer, but not as warm as the rest of the photosphere. And it's actually also to do with the way the magnetic fields are aligned. The magnetic fields in the sun's center of the umbra are typically poking straight up out of the sun. And as they get out towards the edges, they tend to be laying flat across the surface. So they're channeling material along them and outwards in these kind of filament-like streaks. Now, sunspots can be quite small, or they can be really, really large. This one here is an image that shows the Earth to scale. If you look at the sun's disk here, so sunspots are much, much bigger than the Earth. They can come and go over a couple of days or a few weeks. Sometimes they can survive 2 or more solar rotations. So the average Carrington rotation, we call it, is about 27 days. You can see the same sunspot come around several times. You can see things like filaments and light bridges. Sometimes you'll have a sunspot with a really bright line across the middle of it. And that's where the hot plasma is being moved by the sun's magnetic field. Now, sunspots were first recorded in China about 2,800 years ago, but again, they've probably been known about for a lot longer than that. Again, stressing that you shouldn't look at the sun with the naked eye, but when the sun's close to the horizon and behind some fog or a thick bank of cloud, you can sometimes see sunspots on the surface, and that's how the Chinese will have observed it, probably how earlier people will have observed it. There are large sunspots, you can see them with the naked eye. Again, either use your white light filter or your solar eclipse glasses rather than actually relying on that as a safe way to observe the sun. Taking a little bit more of a look at what goes on with sunspots, they appear in pairs or groups of pairs, and one will have a north magnetic field and one will have a south magnetic field. And actually you can see what's going on here in this little diagram I've done. If you imagine there's a bar magnet inside the sun, the magnetic field lines will come out of one pole of the magnet. They poke out through the surface of the photosphere, making this hole and pushing material aside so that no hot material is making it up to the top and therefore darkening it. Then they'll go around a bit and then they'll disappear back out again into the second sunspot to reconnect the magnetic field. So you will always find sunspots traveling in at least pairs or groups of pairs. Sometimes you won't see the second sunspot, and we'll have a look at why later on, but there will always be what we call a leader and a follower spot. But we have what we call the sunspot cycle. So the reason we haven't seen many sunspots for the past 3 or 4 years is that 2 or 3 years, is we've literally just gone through the solar minimum, which happened in December 2019. We now know it takes a few months for scientists to figure out when the solar minimum happened. But we're at the minimum activity of the sun, and we're just starting to come out of that now. And the activity will increase over the next 5.5 years to the solar maximum, and then it will start to decline again. So the sun has an 11-year cycle where activity increases to a maximum, then decreases again, so up and down. And this chart here shows right back to 1870, all of the sunspots that appeared on the surface of the sun. You can see 2 things going on here. You can quite clearly see that the numbers of sunspots, if you look at the count at the chart at the bottom, you can see that there are few sunspots sometimes at minimum and many sunspots at the maximum, and that repeats every 11 years. You can see that the latitude of the sunspots, so this is a chart latitude, this is the solar equator, the middle of the sun, and this is the north and south poles of the sun on this chart. And you can see it over time. At the start of each solar cycle, the sunspots appear nearer to the north and south poles, and as the cycle proceeds, they migrate and appear closer and closer to the equator. And once you get to minimum, they pretty much disappear, and then the whole thing starts again. Now, what happens there is that we'll have a look in a minute. It's caused by the magnetic field. But it's actually a 22-year cycle, although it happens every 11 years. Each time we go through the cycle, the north and south poles of the sun switch places. So you'll have the north at the top and the south at the bottom for the first 11 years. You get to minimum, it flips around, and then you'll have south at the top and north at the bottom, and it just keeps flipping back and forward. So actually, whilst an 11-year activity cycle, the magnetic cycle is 22 years, and that's caused by the way the sun's magnetic field winds itself up, as we'll see in a minute. Now, we know there are longer term cycles in the way the sunspots appear. You can quite clearly see, we go back to 1870 through to sort of the first half of the 20th century, activity was quite low, and then through the 40s, 50s and 60s, it picked up quite a lot, and it stayed reasonably high and then started tailing off again. And recently it starts to be dipping down again. So these cycles were not that active, and then we've had some very active ones, and we've had some dimming, and we're not sure of all of the reasons for this, and there are lots of different theories, and there may be cycles that take place over hundreds or thousands of years that we just don't have enough data on at the moment. Obviously, we haven't been observing the sun long enough to gather that data, so most of the evidence we have is gathered through things like measuring isotopes and tree rings and ice cores and stuff like that, sort of secondary measures rather than directly observing it. So there's a lot to figure out what's going on here. We've all heard of the Maunder minimum. So between 1645 and 1715, there were hardly any sunspots at all. Now, it was suggested that possibly this was the cause of the little ice age as they know it. We had the frost fairs in London where the Thames used to freeze over. I mean, that doesn't happen today, but during that period, it used to freeze quite regularly so that they could have, market stalls and people ice skating on the Thames. And it was suggested possibly this was due to this lack of sunspots. More recently, it's been suggested it's probably also more likely to be due to volcanic activity. There was some major volcanic activity in that period that put a lot of sulfur dioxide into the atmosphere and cooled it down. So what's going on with this solar cycle? Well, this animation gives you an idea. At the start of the solar cycle, the sun's magnetic field is nice and organized, but as each 11-year cycle proceeds, the magnetic field winds itself up. The problem is the sun is not a solid object, so it's not all spinning at the same speed. It's traveling faster at the equators than it is at the poles. It's also traveling faster inside than it is at the surface. Plus, you've also got all these big convection currents inside, looping up and down in the convective zone. So what happens is you get this complex winding up of the magnetic field over the 11-year solar cycle. And when you get to the most disorganized part of the cycle, what happens is the magnetic field is so knotted up, it's poking out of the surface all over the place. And that's what causes the increase in the number of sunspots, because it's the magnetic field coming out of the surface and going back in again that creates sunspots. So as the magnetic field winds up, it gets more disorganized and bits start coming out. That creates the sunspots. Eventually it gets so disorganized that it just breaks down completely and resets itself into this lovely organized thing that we see at the beginning of the animation again, but with the north and south poles reversed. And it does that every 11 years, winds up, breaks down, flips, starts all over again. Now, sunspots take different amounts of time to go around because of this differential rotation. So a sunspot on the sun's equator would actually take 26.25 days to actually get to the same spot. It's slightly less now. I think it's only 23 days for the sun's equator to rotate, but the Earth is also moving around the sun, so the sunspot needs to catch up with us to appear in the same place on the sun's disk. So it's a 26-day period. Now, it all takes much longer at the poles because the poles are spinning much slower. So what we do is we actually use an average of 27.25 days, which we call the Carrington rotation, to measure solar features. So you'll often hear people say the sun takes 27 or 28 days to rotate. It ain't that simple. It's not a solid object. It's going around at different speeds. Right. The other final feature that we can see on the white light sun is what we call faculae. Again, you need a lot of magnification to see this, but again, you can see it in white light. It's easier to see at the edges due to limb darkening, and it's these bright speckles that you can see here. Again, it's caused by magnetic field lines. It's not really a difference in the sun. It's just that the granules, the convection cells, are being lifted up a little bit more. So we're looking through the edges of them into the bright centers rather than looking down on the tops. And these actually increase and decrease from the solar cycle. And actually overall, faculae win out over sunspots. The sun is about 0.1% brighter at maximum, at solar maximum, due to the extra faculae versus making it brighter versus the extra sunspots making it dimmer. So interesting thing to know there. Right, we'll talk a bit about eclipses. I won't go on about this too much because you probably will understand what an eclipse is. The sun will move in front of the moon will move in front of the sun. You can have different types of eclipse. Mostly they're partial eclipses where the sun just appears to graze through, the moon appears to graze through the sun. The next partial eclipses we've got to see from Essex, 10th of June 2021, 25th of October 2022, and 29th of March 2025. And you can see those in white lights, eclipse glasses, whatever you've got very easily. Total eclipses are a lot rarer where the whole moon passes in front of the sun and blocks it out, just because the path of the sun shadow is relatively narrow. It's never more than about 166 miles wide on the face of the Earth. So you've got to be in the right place at the right time. The last total eclipse visible in the UK was the 11th of August 1999, only visible from Devon and Cornwall. On the mainland, my sister-in-law saw it and I was at work, so go figure. Now, the next total eclipse in the UK won't be until the 3rd of September 2081, and only in the Channel Islands, and on the mainland you'll have to wait until 23rd September 2090. And again, it will be South Coast, Devon and Cornwall. There are some convenient ones coming up though. There's another eclipse right across the middle of North America in 2024, April 2024. And the one I'm hoping to be able to see maybe 12th of August 2026. It will be going right across Mallorca and the other Balearic Islands, right across the middle of Spain. And it will be right in the middle of holiday season as well. So I think it could be a great place to go, assuming we're all safe to travel again. And then there will be another one in 2027 that just goes across the bottom tip of Spain. As we said, during the total eclipse, that's the only time you can normally see the sun's corona, which is what we see here. Tenuous outer layers of the sun extending millions of kilometers into space. Sometimes the moon is just a bit too far away from the Earth. We know about supermoons, and we have the opposite, where moons are a bit small because the orbit of the moon is not circular either around the Earth. So sometimes you get what's called an annular eclipse, where the moon doesn't cover the whole disk of the sun. It creates a big ring of fire like that. Well worth trying to see any type of eclipse. Transit of Venus. I think you're a bit out of luck on this one, I'm afraid. The next transit of Venus will not be until December 2117. I don't think most of us will be around then. I was lucky enough to see one on the 8th of June 2004. They come in pairs, and then there was another one on the 5th to 6th of June, kind of overnight, depending on where you were in the world. In 2012, I didn't see that one, but I was lucky enough to see the one in 2004. They are visible through eclipse glasses and naked eye. Not that any of us need to care, because Venus is quite large and reasonably close to the Earth. Very easy to see, but I'd say you'd have to plan on living for a long time to see the next one. Transits of Mercury are much, much easier to see, because Mercury is much nearer to the sun, so it passes in front of the sun with respect to the Earth once, about every 13 or 14 times every century, so a bit more than once every 10 years. I saw one on the 9th of May 2016. I know many of the members of NEAS saw one at Great Notley. I think it was not Great Notley, it was near there on the 11th of November 2019. Next transit of Mercury is the 13th of November 2032. It's a little way off, but not impossible to think about. The only thing, as I say, if you look at these photos that some of the members have seen, Mercury is very, very small. It's a small planet and it's quite a long way away. So you definitely need binoculars or a telescope with a safe sun filter to see it, not visible with the naked eye. Right, we'll quickly move on. Now, with that was all looking at the photosphere and white light. We can also observe the sun in other wavelengths to see other features. Now, the one that we most commonly use as amateurs is hydrogen alpha. This is a red wavelength that's emitted by hydrogen atoms. It's the brightest wavelength that's emitted by ionized hydrogen, and it allows us to look at features in the chromosphere rather than the photosphere. And what effectively is happening is that electrons like to be in particular orbits around atoms. The hydrogen atom has typically normal circumstances one electron, but it can only be in certain states, energy states, and you can see 3 of them depicted here. It can be in energy state 3, 2, or 1. It can never be in any of these places in between. It's not allowed to be by the laws of physics. There are higher energy states it can be in as well. And every time it transits from one energy state to another, because it likes to be at the lowest energy state it can be, it has to get rid of energy. And the energy is emitted in terms of a photon of light. And the photon of light for any transition between states is always the same color, because it equates the amount of energy the electron needs to move as it drops from one energy level to the next. The brightest emission wavelength is hydrogen alpha. It's this red wavelength when the electron transitions from energy state 3 down to energy state 2. There are other hydrogen, beta, gamma, etc. wavelengths that are less bright because the transitions happen less often from different orbits. The reason this one is most interesting is because it always occurs where there's ionized hydrogen. The amount of energy needed to get an electron up to energy state 3 is almost exactly the same as the amount of energy it's needed to actually ionize a hydrogen atom, i.e. let the electron escape completely from the atom. And every time an ionized hydrogen recombines with its electron, the electron will go into a higher energy state typically, and then it will drop down through a number of energy states to get to the lowest state. And about half the time it's doing that transitioning, it will go through from 3 to 2 in one leap. The rest of the time it will bypass it by going from the higher energy to 2 or to 1, or from 3 to 1, or whatever it may be, and getting different colors. But 50% of the time you'll get this transition and you'll get red. So that's why hydrogen alpha light is so bright compared to the other wavelengths. And it always occurs where there's ionized hydrogen. So when you see glowing nebulae in red, nebulae in the Orion Nebula and all those photographs the members take, that's because hydrogen is ionized. You've got electrons being ripped away from atoms. Then when they recombine, they emit red light. And same thing's going on in the sun's chromosphere. To see hydrogen alpha, we need a really good telescope. It's quite tricky because the problem is that hydrogen alpha is quite a bright wavelength. It's swamped out by the broadband, the white light emission coming from the photosphere. It's a bit like trying to see a candle flame against a searchlight. They're both emitting light, but one's swamping the other. So we really, really need to hone in on just that wavelength. So we need a special telescope. And we have various types of solar telescopes to observe hydrogen, but they all basically work on the same principle using what we call an interferometer or an ettalon. Strictly an ettalon. This isn't an ettalon, this is an interferometer. There's a subtle difference between the two, but they work on the same principle. Pretty much all amateur telescopes use an interferometer, which is 2 pieces of glass. An ettalon is 1 piece of glass with the light traveling through it rather than between 2 pieces of glass. And what happens is we basically have 2 mirrors that are really flat and really close together, fraction of a millimeter together. Any light that has a wavelength that is an exact half wavelength is an exact multiple of the distance between the 2 mirrors will have what we call constructive interference. It'll keep bouncing backwards and forwards, and eventually some of it will escape out of the back of the mirror that we can observe it. Any light that has a wavelength that isn't an exact multiple will actually not go through constructive interference, and it's lost back out in the front of the mirror. And typically you have somewhere between about 85 and 90-something% reflectivity on one surface and a bit more on the rear surface, but not 100%. The weird thing is, if you only have one surface, any light that's coming in, if it's 85% reflective, 85% of the light will be reflected out, and 15% will go through the surface into the gap. The minute you put the second mirror in there, through the magic of quantum mechanics, 95% of the wavelengths that we're interested in will go through the first mirror. The question is, how do they know the second mirror is there when they haven't even got to it? That's not one for me. You can ask Jamie that one, but that is the weirdness of quantum mechanics for you. But essentially what we're doing is we're just making sure this gap is the right length for light we're interested in. So really, there's a bunch of different elements in the telescope. I won't go through them all, but effectively what we end up with is, I'll skip this one as well. What we end up with is a series of peaks of light. So this is the wavelengths, the colors along here. This is how much light is transmitted through the ettalon. You have a whole series of peaks that are the right length, wavelength to get through the gap, and then gaps through all the light that isn't the right length. So this is what we call a cone filter. So we have a bunch of peaks coming through. And what we then do is we then have a second cheaper filter with a much wider band pass that only lets hydrogen alpha through. And we put that on the back of the telescope, and that will actually only select out the one peak we're interested in. Now you may say, well, why can't I just use this single filter? This is a bit like the hydrogen alpha filters you use for nighttime imaging and viewing, but even narrower than those, but it's still not narrow enough to actually make the hydrogen alpha features visible, because it's got quite a wide band pass, and actually the peak that we're interested in would be swamped out by all of the surrounding wavelengths, and it would also let through. So we need 2 filters, one to make a really narrow peak, or a series of really narrow peaks at different wavelengths, and then a second one to pick out the one wavelength we're interested in. We also need to tune the Etalon. So we need to, because we make them, but we can't make the gap precisely how we want it to be. One thing, if there's air in the gap, depending on the atmospheric pressure, the distance the light travels will vary due to refraction. So if you've got a telescope you make for using at sea level and then take it up at the mountain where the air pressure is lower, it wouldn't work because the wavelength going through would be the wrong one. So we have to tune it somehow. The simplest way to tune it is actually just to tilt it a bit. And you can see that if you just tilt it, as the light enters the mirror element, it bends through refraction. And the more you tilt it, the more it bends. And you can actually bend it. And eventually the gap gets a lot, because the angle it's traveling through the gap gets steeper, the distance gets longer. You can tune it to be the right length for the light you're interested in. You can do that through tilting. You can also do it through heating. Some telescopes have solid elements. They have a bit of stuff called mica in the middle rather than air. So it's sort of crystal. You heat the crystal, that changes the refractive index. Or and the kind of ones that I like to use, you actually change the air pressure by pumping it up. You have a little piston. You actually increase the air pressure inside the Etalon. That actually makes the air denser and changes the amount the light bends because of the refraction. Makes it denser, so it bends more. But either way, you have to tune your Etalon. If you want to go the big money, what you can really do is you can actually put two filters on your telescope. You can put two Etalons, one inside and one on the front. You get two peaks. And if you offset them slightly, what you actually get is the only stuff that goes through this bit in the middle where the two peaks overlap. And that's actually even narrower than the peak that you would get from a single Etalon. You actually get a much better contrast, but you get a dimmer image. The price you pay is actually expensive because the cost of the second Etalon, because it needs to be on the front of the telescope, is bigger and it's much more expensive. Lots and lots of different telescopes. None of them are cheap, and Daystar do a 600, 700 quid Solar Scout, which is your entry level. Lots of people use the PST. It was great at the time. I think it's kind of had its day, to be honest. I think if I was out in the market for the entry level solar scope these days, I think I would go for a Daystar Solar Scout maybe. An Lunt LS50 is probably the best one out of the three, I would say. About £1,000, depending on the type model that you get. Small, nice views. But if you want to double stack, as we talked about, to get better contrast, the price goes up significantly. Just to give you an idea, something like a PST will give you this view here because the width of the peak that's going through the Etalon is quite wide. You don't get much contrast, but you can see that the prominences are brighter for the reasons we can talk about. If you have a narrower bandpass, you get more contrast. So that basically you get what you pay for. Better scopes with narrower bandpasses tend to give you a more contrasty image. If you want to spend serious money, you can move up to, kind of Quark do hydrogen alpha eyepieces that go on to existing telescopes that you may have. The quality of them can be variable. So if you're thinking about buying one, let's have a chat. The one I've got is one of these Lunt LS60 pressure tuned jobs. I really like it. Very, very good. Somewhere between 1850 and 2700, depending on the price and the size of the blocking filter. And Coronado also do intermediate scopes. If you want to spend serious money, you can. You go much, much bigger, but you're talking £6,000 to £70,000, depending on. Mounts don't need to be that great. Altair's mounts are much easier to use and set up in the daytime because most of them have a daytime or solar alignment option. Equatorial's better for imaging, but there's nothing to polar align on, so it can be quite tricky. But you don't need a big, expensive mount. Just whatever you've got will typically work. So what do we see in hydrogen alpha? Well, if you've got a big scope, bigger than 80 millimeters, but bigger than the one I've got, the first thing you'll see is these things called spicules. They are jets of plasma. They're about 300 kilometers long diameter, moving at about 110 kilometers a second. And they typically last a few minutes each. And the whole of the chromosphere, the layer above the photosphere, is covered in this furry stuff. And the best place to see it is actually along the edge. If you look at the edge of the sun through a good hydrogen alpha scope, bigger than 80 millimeters with a bit of magnification, it looks like clumps of grass growing out of the side of the sun, best seen at the limb. So this is small scale stuff that's going on. It's essentially plasma being moved around by magnetic fields in the sun. Typically through through your oscilloscope, the thing you're going to see of any size hydrogen alpha scope is what we call mottle. It's this kind of very sort of 1970s carpet effect, and effectively it's just bundles of the spicules plus filaments joining together to make this dark and light swirly pattern all over the surface of the sun. It depending on how you process the images, it can look more or less like a swirly pattern. It looks more swirly visually than it does in imaging quite a lot of the time. The other thing you get is feature called plages, beach in French. These bright white areas that don't have any mottle, don't have any spicules. They can last for several days. They're sometimes near sunspots and active regions, sometimes on their own. And again, they're due to magnetic field lines coming out of the sun. Okay. Sunspots can also be seen in hydrogen alpha, and they're much more interesting in many ways. And along with sunspots that create in white light, you can really start to see the magnetic origins of them here. So remember I told you that sunspots always travel in pairs, even if you only see one. What you can see here is a sunspot, and the second place where the magnetic field is going back in or coming out of the sun is here. It's this active region. It's not quite active enough to make a sunspot, but it's definitely there. So in white light, you'd see one sunspot and wonder where the other one was. In hydrogen alpha, you can see that there's definitely something else going on. You can see these curly lines. These are kind of the filaments that join the sunspots where the magnetic fields are traveling along. And the smaller ones are called fibrils, and the larger ones are called active region filaments, where the fibrils bundle together. If we zoom in a bit, what you can sometimes see over the course of a few minutes, you can see things called element bonds and microflares. So this bit here, for example, you can see this flash. This is like potentially an element bond, this little white bit here, or it could be a microflare where magnetic fields kind of reconnecting, letting off a bit of energy. You can definitely see how the plasma is moving along these magnetic field lines from one sunspot to the other. It looks just like iron filings in a bar magnet. So essentially it's the same thing. You know, it's a magnetic field going from one pole to the other, and material aligning itself along it. Between two sunspots, you can often see things called transition arches. They're either darker or lighter areas. They're the same sort of thing as fibrils, but they're a bit more stable. They don't tend to move and change as quickly. This animation is over about 3 or 4 hours. This is not, real time. You can see how dynamic the sun is. The other big thing you see in hydrogen alpha is prominences. These are huge areas of hydrogen that extend into space above the chromosphere. And again, they're lifted up and trapped between magnetic fields, often between opposing magnetic fields that are going in different directions. And this thing called shearing, same sort of thing that goes on in wind when you have tornadoes. Gas gets trapped along the magnetic field lines and lifted up. There are two types of prominences. There are what we call quiescent prominences that are quite long-lived and fairly static. They don't change very quickly. And this is a quiescent prominence here. I know it looks like it's changing a lot, but it's actually, as you'll see in a minute, quite not particularly active. They do change over time, and they can appear and they can disappear. And then you have the second type, which is active prominences that are usually associated with solar flares. Now, there's a whole zoo of prominences and ways of classifying them. You'll see all sorts. We've got hedge prominences, various other curtain, flame and fan, and arch type prominences. The interesting sort of prominences that you sometimes see are these disparition brusque prominences or eruption prominences. Now, they're quiescent prominences. What can happen is if they get above about 50,000 kilometers above the chromosphere, the top of the prominence can disconnect from the bottom and either disappear or zap off into space. And this can be quite dramatic over the course of a few minutes or an hour. So here we've got one in action I caught this year. So this, I think, it's a bit misleading. You may think it's like just a long streak going into space, but what you really need to think about is actually, you see this bit here, it's probably a loop that's going back around the sun away from us. What's happening is the top part is breaking off and disappearing into space. The bottom half just fades away. Now, these can disappear quite quickly, and then they can reappear days later in the same spot. but most of the big prominences that you see that are long lasting are these quiescent prominences. You also see filaments, and again, what you can see here on these are basically prominences that you see face on, so rather than out of the edge, so the same thing, you're just looking down on them. Here's an animation of one again, so you've got a bit of a sunspot here. This is a big quiescent prominence. This is in a negative image, so it's inverted black and white. But it's essentially the same thing. So we've got prominence here, you're looking edge on, prominence here, you're looking down on top of it. The final thing we really see in hydrogen alpha, which is quite exciting, is what we call solar flares. Now at the top here, this is a solar flare that I caught in action a few years back in 2017. It's a class M flare, so flares come in A, B, C, M, and X, and like earthquakes, the A, B, C, M, and X are 10 times more powerful than the previous one. Then you have a number, so an A0 is about not much more than the background strength of the chromosphere. A B0 is 10 times more powerful than that. C0, 10 times more powerful again. The big ones are the M-class flares are not that hazardous. They're quite big and obvious to see, but they only really have minor effects on the Earth unless you're an astronaut. X-class flares are the really exciting ones. They're the ones that actually can do damage on the Earth. The largest flare we saw in modern times was an X28, but it was probably more than that because the sensors blacked out after a while. X-class flares, they actually produce more energy than billions of hydrogen bombs going off at once. So this one here is, let's say, let's go forward again. This one here is a class M, so this is one down from X. And what actually tends to happen is that you have the magnetic field coming out of an active region or a sunspot, as we've seen before, and then you often get a second opposite polarity bit of field poking up, and that tends to cause disrupt the magnetic field, and the bottom part of the magnetic field will reconnect, as we see in diagram 2 here, leaving a big chunk of disconnected magnetic field up in the chromosphere. That's not a state that the magnetic field can be in, so it very, very rapidly snaps into what we call a magnetic reconnection. There's a big explosion of energy, and we get loads of electrons being accelerated to nearly the speed of light, and they all blast down like a giant hadron collider into the surface of the sun, back down into the chromosphere. And as they impact all the material down there, they start shooting off light in every wavelength, from radio right through to gamma rays. And they can be really, really massive explosions. There's also huge electric currents going on. It's heating the plasma as well due to the magnetic fields. Now, the most famous flare was the Carrington event, 1859. It was actually the first one ever observed, seen by Richard Carrington in white light. So you can see them in white light, they're really bright. That was estimated to be an X50 by working back through the data, and that produced aurora that you could see as far south as Cuba and Hawaii. And the magnetic storm that it created on the Earth actually set telegraph wires on fire across higher latitudes due to the electric currents the Earth's magnetic field being disrupted, created. Nothing similar has happened yet in our lifetimes or in modern time, but if it does, I think some people could be in for an interesting time with power cuts and other problems. The grids are designed to try and deal with this stuff, but who knows? It can be very, very massive effects. And what you can see here, again, this is a negative image, so this is where the flare is happening. You've got what we call a surge prominence. This is an active prominence. This jet here of material that's been blasted out. I've got a nice animation of one going on here. This is the smallest C-class flare that I picked up in 2017. It took about 2 hours. There was a bit of a break in the recording, so when it goes from sort of being bright and then suddenly flashes brighter, it's not an explosion, it's just I've got a gap in the image. But if you actually look here, you can see there's a surge prominence that shoots out there, and then the material later on collapses straight back in again along that line. And you can also see at the top here, this is what we call a heteroprominence. That's a quiescent prominence. So you've got the two types, an active prominence and a quiescent prominence. Obviously, you can also see transits of Mercury and Venus in hydrogen alpha. This is the one that I saw in 2016. So, you can see how tiny Mercury is here, going across the disk of the sun. You can capture the space station as well, if you're lucky. If you go to transit-finder.com, That gives you predictions for ISS transits of the sun and the moon. You can also get easyJet transits if you're really unlucky, like I did once. Can't really plan for those. Imaging in the hydrogen alpha, it's similar to planetary, really. How I get those images, really just use something like fire capture, really short exposures, loads of them, and then you stack them in auto stack it like we've been practicing in our Imaging Wednesdays meetings, then just do a bit sharpening and deconvolution. You want a mono camera if you're doing hydrogen alpha, because white light you can use a color camera, but hydrogen alpha you want a mono camera because the light is red, so only a quarter of the pixels will pick up the red light if you've got a color camera. So you really need a mono camera. Get as many frames as you can, but you really need to keep the exposures down to about 30 seconds because the sun is so dynamic that if you expose for longer than that, you know, your video is more than 30 seconds, actually stuff is moving and it gets blurred. Animations is just the same, it's just horrendous. You literally just take a 30-second video every 30 seconds to every minute. You do need to track the sun quite accurately, and then you have about a month of processing the data because you've got to stack every single video. You've then got to align all of the individual output frames and then turn them into a video, and you need a massive hard disk as well. But you can do it. If you don't have a solar telescope, loads of websites online, you can see solar stuff. The NSO GONG network just gives you real-time round-the-world views of the sun in hydrogen alpha. Solar Dynamics Observatory gives you views of the sun in loads of different wavelengths, white light, hydrogen alpha, and lots of other interesting stuff in near real time at very, very high resolution. And they do some lovely animations like this one you can see here. You can observe the sun in other wavelengths if you want to spend a bit more money. So you can observe photosphere in calcium. Typically the K filter is calcium K line. It's similar to the photosphere, similar to white light, but some of the features are more contrasted. Calcium shows more granulation, but you know, again, it's a bit more advanced, and you really need to sort of get some advice and consult your retailer if you're going to buy something, because a lot of these filters need specific scope setups to work well. Okay, that's it. So for the people watching on YouTube, if you've got any questions, either post them in the comments or contact us via our website, northessexastro.co.uk, or find us on Facebook, Twitter, etc. For the members, what we'll do now is we'll end the live stream and we'll switch on our cameras and have any questions on Zoom. So I hope you enjoyed that, and thank you for listening. Okay.